A line integral is something that can be used to calculate the area between a surface function and a curve in two-dimensional space that is below it. So here we have a surface function, z is equal to f at xy, and let's think about some curve c that lies here down in R2. And let's think about flying each of the points on the curve c up to the surface to see what their corresponding outputs are. We can think of this as a curtain-like shape, and a line integral is going to give us the area of this hanging curtain. In order to derive the formula that we're going to use to calculate the line integral, the idea is that we're going to look at an ith subinterval and a representative within that ith subinterval, which is some domain element, and the corresponding output of that domain element up on the surface. So the height of that approximating rectangle is the function value. And let's say the width of that rectangle is a small change in s, where s is the length of the arc along this curve c. So we'll say delta s is a small change in the arc length, and that's what we're going to use to get the width of the rectangle. Once we have that width, we can multiply the width and the height together to get the area of this hanging strip. And then we can add together infinitely many of those to get the total area of that hanging curtain. Basically, this is the height of an individual strip multiplied through by its corresponding small change in the arc length. So this is more of a theoretical definition for the line integral. Now we need to work with it in order to come up with an equation that we can use to actually calculate this area. So let's consider this curve c in R2, and let's let r of t be the vector function that represents that curve. Let's also say that t is equal to a is the value of the parameter that begins the curve, and that t is equal to b is the value of the parameter that ends that curve c in the floor. Now, in order to determine the arc length of a curve, we use the formula, the integral from a to b of the square root of x prime at t quantity squared plus y prime at t quantity squared. And we can essentially use this formula in order to plug in for the ds, small change in arc length, in our integrand. To get the integral from a to b, we're going to need to have the function value that gives us the height of the approximating rectangular strip, and then we multiply that by, essentially, this arc length formula. Now we'll need to continue working with this just a little bit more because we're integrating here with respect to t, so we need to substitute in for these x and y's. Since x and y are on this curve, they're also functions of that parameter. So we can substitute those parametric equations in for x and y to get an integral now that depends entirely on t. So when we have a 3D surface and a two-dimensional curve C in the xy plane over which we're integrating, this is the formula that we're going to use to calculate that line integral. Now, we can duplicate this process for higher dimensions. Let's consider some curve C in three-dimensional space, where this curve is represented by a three-dimensional vector function. And we'll also consider a small chunk of this curve, whose length is a small change in S, or a small change in the arc. So an xyz ordered triple in this subinterval would be considered a domain element plugged into a four-dimensional function. And let's think of that range element as giving us kind of the conceptual height that can be multiplied by that arc length, which then gives us the value of that line integral. Now, each of the x value, the y value, and the z value on that curve is itself a function of t. So those parametric equations are going to be plugged in order so that we can get an integral that's entirely in terms of t. And so this would be the formula we're going to use to evaluate that line integral.